Langlands program, yes, indeed, I would say it has been one of the main themes of my research since like forever. It's a vast subject and fascinating subject. So I want to tell you a little bit about it. I want to start out with this quote. I wrote this book. It was published in 2007. Langlands correspondence for loop groups. Now, correspondence here doesn't mean correspondence in the sense of sending letters to each other, although Langlands and I have done that a lot over the years. Here, correspondence means a kind of a relation, like one-to-one correspondence or something like that. So in the preface, I say, the Langlands program has emerged in recent years as a blueprint for a grand, unified theory of mathematics. And I have to confess, I said it a little bit tongue-in-cheek, you know, because in mathematics is not like quantum physics, or, you know, where one can talk about the grand unified theory because you have certain interactions with certain forces and you want to find one underlying theory describing all of them. Mathematics is just too vast to have one all-encompassing theory, you know. But if there were one, the Langlands program would probably come closest. So interesting enough, this phrase, grand unified theory of mathematics, has kind of caught on. And in fact, if you look in the Wikipedia article, you will see it quoted as well. So now let's try to live up to the expectation.
I have one question first.
Okay.
Why is it called Langlands?
Langlands.
Yeah, Langlands is a person?
He's a person, this guy. Look, he is a very interesting man, Canadian-born. He is professor emeritus at the famous Institute for Advanced Study in Princeton, New Jersey. The institute which, you know, had as its professors people like Albert Einstein. In fact, Langlands has Einstein's office. And in this picture, he is at his office, which is formerly Albert Einstein's office. A very nice office, I might add, you know. I have collaborated with him, so I had a privilege, I had a chance to spend some time in that office. Langlands program is named after Robert Langlands, because he was the one who came up with these ideas, or the first set of ideas that we now call the Langlands program, in the late 60s. Now, what happened is that these ideas actually propagated to other areas of mathematics, and that was due to research by other people, not necessarily Langlands himself. And I think that's why so many mathematicians are, and quantum physicists these days as well, are so excited about this project, about this theory. The fact that there are certain patterns which one can observe in many different areas of mathematics, such as number theory, harmonic analysis, geometry, and now even quantum physics. To set it up, I want to say that, to me, mathematics is something like a kind of like a giant jigsaw puzzle. Suppose that you are solving a jigsaw puzzle, but you don't know what the final picture is going to look like. It's kind of harder but more interesting, because then the picture will gradually emerge. But usually people start, you know, finding pieces that fit together and so on. And so next thing you know, you have several islands or continents of sorts on the big table. You just throw the pieces on the big table, and then several people start working on this. That's kind of like different areas of mathematics. Sometimes I use another analogy. I say the continents of mathematics. So what are they? For instance, number theory. The study of numbers and equations, like the ones which we'll talk about in a moment. There is also another field called harmonic analysis, which is like trying to decompose a sound of a symphony into the kind of elementary harmonics, into the notes played by different instruments. And that idea has found sort of a great following in mathematics, where you kind of generalize it to much more general situations rather than sound. There is also geometry, obviously. We all study Euclidean geometry in school, but in fact, this is just one small example. There is also non-Euclidean geometry. There are all kinds of geometries in higher dimensions. There are different shapes and manifolds that we call them, and so on. So there are all these islands. As you know, when you are working on a puzzle, the most exciting moment is when you can connect those islands that you have built. And that's what the Langlands program does. It connects different branches, different islands, or different continents of mathematics. And specifically, he started out with some difficult questions in number theory of the kind that we will talk about in a moment. And he was able to connect these questions to questions in harmonic analysis that have to do with analysis, with functions, with kind of like things that we study in calculus, so kind of totally different domain, right? And The beauty of it is that the original questions seem to be intractable, seem to be extremely hard, unsolvable almost. But when you translate them into this other domain, harmonic analysis, they have much nicer structure, and there are tools of harmonic analysis which enable us to solve them. So there is a practical advantage of this type of approach, because problems that up until then could not be solved, suddenly you find a way to solve them, and not just one specific problem, but a whole host, a whole class of problems of that nature, you see. So that's why people got so excited about it. And then they got even more excited when these ideas propagated to other fields like geometry, and then more recently quantum physics. So, but historically, Langlands came up with this when he was a young man in the late 60s, and in fact he formulated his ideas for the first time in a letter to another mathematician, a sort of a maestro of mathematics, André Weil, who was a professor in Princeton at the time. I will read it for you. He says, "Professor Weil, in response to your invitation to come and talk, I wrote the enclosed letter. After I wrote it, I realized there was hardly a statement in it of which I was certain. If you are willing to read it as pure speculation, I would appreciate this. If not, I'm sure you have a wastebasket handy." Kind of an understatement of the century, So
Is he being humble, or do you think he was not confident?
I think he was being humble. I think he knew the importance of it, but he kind of wanted. It's a bit of a show off, I guess. It's like, nah, it's not that important,
We call that a humble brag now, don't we?
I guess so.
Okay.
So that's how the Langlands program was born. So in the set of those notes. And then soon enough, he wrote a paper and so on, and a lot of people found out about it. And those letters, this is late 60s, so it's before the internet. So people were making Xerox copies of this letter and sending to their colleagues and friends around the world. And within 10 years, hundreds of people working in this area. So now, after all this build-up, right? Now, finally, I have to show you what it is about. And usually, like, time's up, okay? So Saved by the Bell. But
no, you can have all the time you want, Professor.
Yes, I will. I will explain it. So I would like to give an example of this, what appears in the Langlands program. That type of connection between problems in two different fields, number theory and harmonic analysis. And the example I'm going to give is interesting for various reasons. One of which is that actually it is precisely the key result that was proved by Andrew Wiles and Richard Taylor to provide the final step in the proof of probably the greatest unsolved problem in mathematics, which had been solved by those papers, namely Fermat's last theorem. You look at the equation a to the n plus b to the n equals c to the n, where n is an integer greater than 2, and a, b, and c are relatively prime, non-zero integers. Now, if n were 2, then we know many examples of solutions of this equation, like 3 squared plus 4 squared is equal to 5 squared. But Fermat believed that this equation for n greater than 2 does not have any integer solutions. So an example would be a cube plus b cube equals c cube does not have a solution a, b, c in non-zero integers. Obviously, if you allow one of them to be 0, you could have a is equal to c and b is equal to 0. So they have to be non-zero to make it interesting, right?
So the theorem. What did Fermat said? You can't do it.
So Fermat famously wrote about it on the margin of Diofanto's book about integer equations, saying that he found a beautiful proof of this theorem, but the margin of the book is too small to contain it. But because he claimed that, Pierre Fermat, a great French mathematician in the 17th century, for about 350 years, people were searching for the proof. Even though, I guess after 100 or 200 years, it became clear they probably didn't have it. Either he was just being provocative, or he was mistaken. We don't know.
Or he got it.
Maybe he got it. Who knows, right? Yeah. But in any case, the fact that he claimed that to have found it, I think, was a great accelerator of the whole field, because people really wanted to reproduce his proof. So eventually, it was actually proved by in a very complicated way. Not by, nobody was able to find a kind of elementary proof where basically you take b to the n to the right hand side and then write as a product of something. It doesn't work. It doesn't seem to work. So instead, mathematicians were able to relate this statement to another statement, which is much harder to formulate. And that statement is called Shimura-Taniyama-Wei conjecture, after three great mathematicians. So Wei, Andre Wei, is the one to whom Langlands' letter was addressed. He had an important part in this project as well. And Shimura Taniyama were these great Japanese mathematicians. So they had this conjecture, which has to do with mathematical objects which are called elliptic curves. And so now you have two different conjectures. There is Fermat's last theorem. Well, we call it Fermat's last theorem because he claimed to have proved it. These guys did not claim to have proved it. They were honest about it. They did put it out as an open question. And in mathematics, we call open questions conjectures. Those were two conjectures, Fermat's last theorem and Shimura-Taniyama-Wei conjecture. And so the decisive step in the proof of this was made by my colleague here at Berkeley, Ken Ribbett, who I believe has been interviewed by Numberphile as well. He showed that Shimura-Taniyama-Wei conjecture implies Fermat's last theorem. So then the search was on for a proof of this conjecture, because people knew that as soon as you prove this one, you get the big prize, right? It's not one of those Millennium Prizes, for the simple reason that Millennium Prizes were created after this theorem was proved. But if Millennium Prizes were created before, then Andrew Wiles and Richard Taylor would collect $1 million. I'm sure it would have been included on that list. But it was a big prize, and it is a result which is probably the most famous of all mathematical theorems. It stood for more than 350 years, so that's quite something. These days, I would say Riemann hypothesis is the big prize, but it was formulated by Riemann at the end of the 19th century, so it's a much younger problem compared to Fermat's last theorem.
So Ken Ribbett's accomplishment was basically showing there was a bridge between the two.
That's right.
And so the race was on to do this one because you got that one for free.
Exactly. Because Ribbett established this already. And that was a big deal. This was in the 80s. So then, now, what's the connection to the Langlands program? The connection is that this can be viewed as a special case of Langlands. Now, when we say Langlands program, we are referring to the whole set of ideas. But one of the central ideas of the Langlands program is what's called the Langlands correspondence. So it is about a correspondence, that is to say a relation, like one-to-one correspondence between objects of different kind. And Shimura-Taniyama-Wei conjecture can be seen as an example of that Langlands correspondence. So let's talk about Shimura-Taniyama-Wei conjecture. I want to give an example of what the statement of this conjecture says. And to formulate it, I need to remind you something which is called clock arithmetic. Normally we do addition, multiplication of integers in the usual way. But for instance, when we talk about time, we here in North America we identify 30. We don't say 13 hours. We say 1 p.m. Right? And so we don't say 14, but we say 2 p.m. So in other words, we identify numbers which are related by 12 or a multiple of 12. That's why it's called clock arithmetic. Normally we have 12 hours. Well, in Europe it would be 24, I suppose. So, but still you do modular 24. It's called modular 24, clock arithmetic. But instead of 24, we could take any other whole number. And especially it's interesting is to consider the case when that number is a prime number. So here's an example where you have a clock which has 7 hours, right? So you identify -7, 0, 7, 14. You identify 1, 8, 15, and so on, right? And so on. So this can be done for any prime number, 11, 13, and so on. So now, suppose you have an equation. Here's a prime example. A prime, no pun intended, example of an equation that is relevant to the story. Remember, I was talking about elliptic curves. So elliptic curves is kind of a fancy name for equations of this type of equations in two variables, x and y, for which one of the variables appears in degree 2 and the other variable appears in degree 3. Like here, on the left-hand side you have y squared as the highest power of y. On the right-hand side, you have the cube of x as the highest power of x. So this equation defines what's called an elliptic curve. Now, why is it called elliptic curve? Well, if you look, and this probably I should say it, kind of slow down a little bit and say it more precisely. One of the main ideas that emerged in mathematics in the last 100 years is that, in some sense, equations are more important than solutions. It's kind of interesting because I think a lot of our teachers should learn from that, because the emphasis in our schools, I think, is too much on solving things. And solving means the easiest way to solve is to memorize the formula. And that's why so few people actually have good experience in their math classes. But if you realize that professional mathematicians actually care about equations a lot more than solutions, then this would help you to kind of refocus completely and reorient the teaching and learning process. Now, what do I mean by equations? Equations matter more than solutions. Because once you write an equation like this, you can talk about its solutions, but you can talk about its solutions in different domains. For instance, you can ask what are the values of x and y in whole numbers so that the left-hand side is equal to the right-hand side. That means you look for solutions in integers, we say, or whole numbers, right? But you can also look at solutions in real numbers. You can also look for solutions in complex numbers. And in fact, if you look at the solutions of such an equation in complex numbers, you will find that the set of all solutions can be presented as a torus, as a kind of surface of a donut. And that's what, it's an example of what's called a Riemann surface. And you know, I always say that it's a Homer Simpson's favorite Riemann surface. This Riemann surfaces, the tori, they are called elliptic curves. So that's where the name comes from. It comes from the solutions of this equation over complex numbers. But for this story, we are going to be interested in solutions of this equation modulo a prime number. You see, so in other words, we are looking for x and y, which are integers, whole numbers, such that the left-hand side is equal to the right-hand side, but not on the nose, but in the clock arithmetic with respect to a given prime number. So for instance, if we are doing it for prime number 5, it would mean that we only need the left-hand side to be equal to the right-hand side up to a multiple of 5. So for instance, if they're equal up to 20 or up to 15 or -5 and so on, we will call it a solution in that numerical system.
Are you saying that we would find the solutions, take them out, convert them into modulo 5, and that's what we're interested in? Or are we only allowed to take the modulo 5 numbers to start with as
That's
our
right.
contenders?
That's right. So first of all, as contenders, let's say if it's modulo 5, we should only consider the numbers 0, 1, 2, 3, 4, both for x and for y.
So you're really narrowing your options.
So there are only 25 options. And then you can just calculate on a piece of paper what happens when you substitute, you know, x equals 0, y equals 0, x equals 1, you know, y equals 0, and so on. And you go through all of these 25 cases. And in some cases, the left-hand side may be equal to the right-hand side on the nose. Like, for instance, if you say x equals 0, y equals 0, you see that both sides are equal to 0. So that's a solution for sure. Not only modulo 5, but in fact, for integer solution, right? Or you could take, for instance, 4 on the left-hand side, and then if you calculate, you get 4 squared, which is 16, plus 4, and that's 20. And 20, for our purposes right now, is the same, as good as 0. So in fact, I have listed here all the solutions. Out of 25 options, out of the 25 possibilities, namely x and y being between 0 and 4, we find actually there are 4 pairs, x and y, for which the left-hand side is equal to the right-hand side, sometimes on the nose, and sometimes up to a multiple of 5. So for instance, x equals 0, y equals 0, both sides are equal to 0. X equals 1, y equals 0, both sides are equal to 0, so these are obviously solutions. X equals 0, y equals 4, that's the one which I mentioned, where you have left-hand side is 20 and the right-hand side is 0. But that also qualifies as a solution in our current framework. 20 is the same as 0 according to clock arithmetic modulo 5, right? And finally, we also have x equals 1, y equals 0, where we also get the left-hand side is 20 and the right-hand side is 0. Again, it is a solution. So we have 4 solutions modulo 5.
So even though we had limited contenders, it also was becoming easier because we were becoming a little bit looser as what equals means.
That's right. Yeah. That's right. So, but you see, that it's a really a kind of a problem that elementary school student can solve. You know, it takes time. So here you would have to check 25 options and see for which of those options the left-hand side is equal to the right-hand side up to a multiple of 5. If you go to the next prime number, which is 7, you would have 49 options, which is 7 times 7. You would have 7 possibilities for x, 7 possibilities for y. Then it's more difficult, so it will take you longer, but you can do it on a calculator, or you can program it. You can have a simple program which can do it for relatively high prime numbers fairly quickly. So here I have compiled the list. On the left column, you have prime numbers, 2, 3, 5, 7, 11, 13.
That's our clock.
These are how many hours we have in our clock. We live in a strange kind of like wonderland where we have not 12, but let's say 7 hours. Or I would prefer 13, so the day would be longer, right? So and then how many solutions? So we just saw that for prime number 5, there are 4 solutions. It turns out that for prime numbers 2 and 3, there are also 4 solutions for each. For prime number 7, there are 9 solutions. For prime number 11, there are 10 solutions, 13, 9 solutions, and so on. Remember, we are talking about the same equation. But in accordance with what I said earlier, you can have just one equation, but it can have solutions in different domains or in different numerical systems. Here we have one equation, which can be viewed as an equation with respect to the clock arithmetic modulo any prime number. So there are infinitely many possibilities of what we could mean in this context by a solution. So if you say, solve this equation, that's not a correctly phrased question, because then you can ask back, in which domain? And so in fact, there are infinitely many possibilities here, and they correspond to the choices of prime numbers. But for each of those primes, there is a well-defined number, the number of solutions, and you can see that it kind of grows, so the prime numbers grow, and the number of solutions grows. So in fact, it turns out...
It dropped again, though. For 13, it dropped.
It dropped a little bit, but if it's possible to compile a much longer list, and you will see that it kind of grows. It's almost equal to P itself, but with some small defect. So that's why it's actually useful to consider not the actual numbers of solutions, but the kind of a defect, the difference between the prime number itself, P, and the number of solutions that you have modulo P. So then you see, for instance, if prime is 5, we found that there are 4 solutions, so this number is equal to 1, because 5 minus 4 is 1. Likewise, for 7, you have 9 solutions, so suddenly it's a little bit larger than the prime itself, so that defect is actually going to be a negative number. So these defects could be both positive and negative, but they're going to be fairly close to 0. They're not going to grow as fast as P, whereas these numbers grow as fast as P. So it's kind of a useful renormalization, if you will, relabeling of things. So now the question is, what are these numbers? And from what we have said, they look completely random. And this sequence looks completely chaotic. There is no, this is too short a sample to actually make any conclusions. But obviously, we can write a short computer program.
So I could put them on the screen.
You could put them on the screen, the first 100 or whatever, right? Oh, but wait, if you do it directly, right? So if you do it directly, you see that it's a hard problem, because each time you have to set up a new problem. Because, for instance, you go from 5 to 7. The results about prime number 5 have no bearing on the results for prime number 7, unless you have found some solution for which the left-hand side and right-hand side coincide on the nose, and not up to a multiple of a prime. So then, of course, such solutions would be valid for every prime. But there are very few of those. So in fact...
Oh yes, because every equation will have a different fingerprint, won't it? Like here.
That's right, because when we talk about solutions modulo 5, we saw that there were 4 solutions. Only 2 of them were solutions where the left-hand side is actually literally equal to the right-hand side. And for 2 other solutions, the 2 sides differed by 20, which was a multiple of 5. But 20 means nothing for modulo 7. It's not equal to 0 modulo 7, obviously. If you have something divisible by 5, it's not going to be divisible by 7. In principle, because they're both prime numbers, right? So for 7, you have to redo the whole calculation from scratch. Then, just as when you kind of like, you're tired and you're sweaty from that, you say, okay, now do it for prime number 11. So again, you have to do it from scratch, right? So you have infinitely many computational problems which a priori looks like have nothing in common, and the numbers that you get look completely random. So what if we could find another way to solve it? What if I told you that there is actually a totally different approach to this problem, where all of these numbers could be written sort of in one stroke? That's what the Shimur-Tanyama-Wei conjecture says, and that's what the Langlands program in general, the Langlands correspondence in general says. It enables you to express the solution of this seemingly intractable problem in number theory by tools of harmonic analysis.
I realise that the 2 columns are very, very linked to one another, but are you talking about trying to spit out column 2 or column 3?
Column 3. So column 3 is a little better, because it's kind of, you have things which are kind of average to zero, so to speak, as opposed to growing as a prime number grows.
So column 3 is where the meat is.
Where the meat is. So the question is to find a way to express all of these numbers for all primes all at once by some magic, by some miracle. So now I want to describe this alternative solution, which pops out completely out of the blue. So there is nothing in the original problem that could suggest that there is a way to solve it in this way. So this is a kind of insight. This is something which, to me, I still think we don't really understand why. We can prove it now, but I still consider it as a sort of a miracle, as a kind of black magic, honestly. Okay, so here's how it works. The claim is that you can write a certain infinite series, and I will explain what I mean by this, in this variable q. Q is like x, but we already have x in the equation, so we just need a different letter. And so traditionally, mathematicians use letter q, but it's just a notation. If you can use x or z or whatever you like. So there is this thing which is called infinite series, which is written as this infinite product, and I will explain what it means, which has the following property, that if you open, it has sort of very regular behavior. I'll explain what I mean by that. And then you can start opening the brackets using the traditional rules of how you multiply, various expressions of this sort. When you start opening the brackets, you're going to get an expression which involves various powers of q, and there will be some coefficients appearing in front, which will be whole numbers, positive or negative. And I claim that if you look at the power, for example, the fifth power, the coefficient will be equal to exactly that number in the third column, associated to 5. If you look at the coefficient in seventh power, you will get number -2, which was the number that we had in the third column associated to 7. And if you look at the 11th power, you get coefficient 1, which is exactly what you get from the counting problem, right? And if you look at number 13, let's hope that this is correct. Yes, it is 4. And so on. So this one line of code, if you will, if we take the coefficient of q to the power p is a prime, so like q to the 5, q to the 7, q to the 11, q to the 13. If you take the coefficient in front, because each of these powers gets multiplied by something, and call it b of p, then a of p, which I recall is the number which appears in the third column earlier, it will be equal to b of p for all prime numbers. So you see, it's like forever. And there are infinitely many primes, as we know, right?
Yeah.
So it is a solution not to 1, not to 5, not to a billion problems. It's a solution to infinitely many problems in one line. It's a kind of a one-liner. It's like if it were a stand-up comedy act, so it would be like, that would be like the one-liner of all one-liners, which would contain all the jokes that was ever told and that will ever be told forever and ever.
As the prime numbers get really, really big, as prime numbers do those coefficients, do those numbers in column 3 stay around the vicinity of 1 and 3, or do they start getting bigger?
They will grow, but they will grow as a square root of p, not as p. So it the growth is much slower.
But they do get big.
They do get bigger, yes.
Yeah, okay.
And they can be both positive and negative. So they are they more or less average out to 0, but occasionally they can become large positive numbers or large negative numbers, but always within the square root of p. Where p is the prime that we're talking about, right?
Okay.
So colossal compression of information. It's like it's like we're literally finding order in what appeared to be a completely random sequence of numbers, a completely chaotic sequence of numbers. And so another way I like to say is it's like one line of code gives us a simple rule which kind of generates the DNA of the counting problem.
It feels magical to me, except I don't know where you got that original algorithm from.
That's right.
Yeah.
That's right. So now I want to explain what I mean by this series, first of all. So to explain, as a warm-up, let me talk about this concept, which we call in mathematics generating function. So if you have a sequence of numbers, so this will be number n, natural numbers, 1, 2, 3, 4, 5, 6, and so on. Suppose that you have a certain number assigned to each, so f of n. So the simplest sequence could be just 1, 1, 1. You assign 1 to all of them. That's the first example. So then mathematicians have this trick where they say, I don't want to look at this table. Instead, I convert it into what's called a generating function or generating series. And so what this is I will take f of 1 multiplied by q plus f of 2 multiplied by q squared, f of 3 multiplied by q cubed, and so on. Or, we like this notation sigma for the summation sign, and we'll say that we just go from 1 to infinity, and we put f of n times q to the n. So what will this generating function be in our first example, where we assign to every natural number just number 1? It will look like this: a q plus q squared plus q cubed plus q to the 4th, and so on, right? So you see, well, there's not much of an improvement in some sense, because here you look vertically, kind of you go down vertically, here you go horizontally to the right. But you can play with this. We can rewrite this generating function in the following way: as q times another generating function, which now starts with 1 plus q squared, and so on. Clearly, if you open the brackets, this term will give you q, this term will give you q squared, this term will give you q cubed, and so on. Each number in the sum is equal to q times the previous number. And we know that if absolute value of q is less than 1, this series actually converges to 1 divided by 1 minus q. So that means that if in this original series, q was just a bookkeeping device. It was just a variable, kind of indeterminate. We don't want to initially assign any value to it. But then we notice that, in fact, this expression, this infinite sum, makes sense if instead of q we substitute an actual number, let's say a real number from -1 to 1. Or it could be a complex number with absolute value less than 1. Then the series actually converges. Converges for real, not like 1 plus 2 plus 3 plus 4, where it actually diverges, but then there are ways to extract sort of meaningful value. Here it actually converges according to all the rules. And so to this function 1 divided by 1 minus q, so that this expression becomes q divided by 1 minus q. So you see, instead of this infinite table, we end up with this very cute looking function. So it contains information about those numbers, f of n, in the following sense: that if you expand it in powers of q, that is to say reverse this process and go from 1 divided by 1 minus q to this infinite series, then you get this series, and from this you can read off all the coefficients f of n, which in this case they are trivial, kind of they're all equal to 1. So that's the first example. Let me give you one more example. Suppose that you assign numbers not just ones, but 1, 2, 3, 4, 5, 6, and so on. So then you're going to have a q plus 2q squared plus 3q cubed plus 4q to the 4th. So it's a little bit more interesting now. And so you say, okay, is it possible to also convert it into something like this? And the answer is yes. In fact, you can, because you can also rewrite it as q times 1 plus 2q plus 3q squared, and so on. I claim that, in fact, this green series in brackets is the derivative by respect to q of this series, because when we take derivatives, we are just doing it term by term. So 1 is a constant, its derivative is 0, so it will give nothing. Q will give you 1. The derivative of q is 1 with respect to q, right? This is ddq, okay? So q will give you 1. Q squared will give you 2q. Q cubed, the next term, will give you 3q squared. And you see that it's exactly the pattern that you get. Each coefficient is going to be an integer, 1, 2, 3, 4, because when you take the derivative of q to the n, you get n times q to the n minus 1. Now, what it suggests is that this sums up to the derivative of this. And for those who remember their calculus course, they will immediately see that it is 1 divided by 1 minus q squared. So you see the result here. So the result in the previous example, when all the numbers were equal to 1, now will be q, in that case it was q divided by 1 minus q, but now it's going to be q divided by 1 minus q squared. So again, you have a very compact expression which contains information about those numbers, which in this case, if you reverse the process and you expand this back into a generating function, you will see 1, 2, 3, 4, and so on popping up as coefficients in front of the corresponding powers of q. So these are two basic examples of the generating function. And now the function that we have here, which appears in the solution of the counting problem, is kind of like that, except it is written, well, you see, here in our basic examples, we were able to write things in terms of kind of some simple factors, where we used actually geometric progression. So in fact, here it was essential that absolute value of q was less than 1. In some sense, this is very similar, because except now we have only positive powers of things like 1 minus q or 1 minus q to the 11. But the meaning of this expression is very similar to what we have just discussed. It is something that could be converted into a series of the form f of 1 times q plus f of 2 times q squared plus f of 3 times q cubed, and so on, by simply opening the brackets. So for instance, in this example, f of 1 is equal to 1, f of 2 is equal to -2, f of 3 is -1, and so on. Now, you may ask, how do I go from this line to this line? Simply by opening brackets. So you see, first of all, there is some regularity in this. What is the regularity? So there is a coefficient q, which is kind of familiar to us now because in our basic examples we also had a q as a factor. Next it comes 1 minus q squared. We know how to open brackets. 1 minus q squared is simply 1 minus 2q plus q squared, right? So then we replace this expression by 1 minus 2q plus q squared. Likewise, 1 minus q to the 11 squared is 1 minus 2q to the 11 plus q to the power 22. So we replace that square by this expression. Then again comes something similar, minus q squared. So you see the regularity is twofold. So to write down this generating function, first factor is q. After that, I write factors 1 minus q squared. Then I leave some space. Then I write 1 minus q squared, and I leave some space. Then I write 1 minus q cubed squared. You get the idea.
Yeah.
And then in these spaces, I write something similar. I write 1 minus q to the 11 squared. Then here I write 1 minus q to the 22. 22 being, of course, twice 11 squared. Then I write 1 minus q to the 33. Always squared. And there are two sequences. One is where you have 1 minus q, 1 minus q squared, 1 minus q cubed, and so on. So clearly the next one is 1 minus q, so square, cube, fourth, squared. And after that, the red one is going to be 1 minus q to the 44 squared, and so on, right? So that's clear. Now, when you open the brackets, you may be wondering whether it is legitimate because there are infinitely many terms. But because the powers of q are increasing as we throw in more and more factors, you can see clearly that when you open the brackets, the only finitely many factors will affect the specific power of q. For instance, if you're interested in q squared, it will come from here, it will come from here, but this is already q to the 11. It's not going to contribute to q squared. Likewise, if you want, q to the power fourth or fifth, these terms will not affect it. So only finitely many factors of this infinite product will contribute to a specific power of q. That's why it is well defined. So the only thing that you need to do here is just open the brackets. And here I give the expression for the first few terms up to q to the 13. And so the statement of this Shmur-Tanyama-Wei conjecture in this particular case is that if you focus not on all coefficients, not on all powers of q, the way we discussed in our basic example, but only on the prime powers. So you look just at the coefficients in front of q squared, q cubed, q to the 5th, q to the 7th, q to the 11th, q to the 13, and so on. What do they all of them have in common? They are all q to the power p, where p is a prime number. Then each of these monomials, each of these powers, will come with a coefficient. So the coefficient, I call this b of 2. I will call this b of 3, b of 5, b of 7, b of 11, b of 13. And the statement is that this, for every p, and p being a prime number, b of p is equal to a of p, which gives the solution of the counting problem for that prime number. Namely, I recall that we are talking about the third column, so a of p is not exactly the number of solutions, but it is p minus the number of solutions.
It's that difference.
Mod p. So all of these numbers, which, well, if you know this, guys, you know obviously numbers of solutions because you simply take p minus that number, right, to get the number of solutions. So all of these numbers can be found in one stroke, so to speak, from the coefficients of this one generating function. Now, what is the meaning of this function? Where does it come from, right? So and it turns out that this is an example of what is called a modular form. So in fact, this example illustrates the general principle that we can link elliptic curves. Remember this equation, cubic equation that we talked about, corresponds to the mathematical object we call an elliptic curve. And so this elliptic curve, like more precisely counting problem, counting points on an elliptic curve modulo prime numbers can be linked to a modular form in this way, that the coefficients of the modular form give us more or less number of solutions modulo prime number up to some simple replacement. And that statement is the statement of the Shimura-Taniyama-Wei conjecture, which is a special case of the Langlands correspondence. And that is the statement which gives us the proof of Fermat's last theorem.
Okay, nice.
Speaking about elliptic curves, I want to mention these two books. So this one called Elliptic Tales, Curves, Counting, and Number Theory, so which talks about a lot of the things that we discussed today, what these elliptic curves look like, and their solutions in different numerical systems, and so on. So it's a really nice book, explained in fairly, understandable way. Okay. And I think will be interesting to both mathematicians and non-mathematicians alike.
We'll link to it. We'll have a link in the notes.
And then the other book is about cryptography using elliptic curves. So the elliptic curves have recently found real-world applications to cryptography. And also, I want to mention in this regard that my very first video for Numberphile was about an algorithm. Actually, it was not an encryption algorithm, but it was an algorithm for generating pseudo-random numbers. That this algorithm was proposed by National Institute for Standards and Technology in the United States. And then when Snowden revealed various documents of NSA, then people found out that actually that algorithm was had a backdoor installed by NSA. And this was important because those pseudo-random numbers were used to generate passwords and things like that, various numbers which were used in other algorithms. So whoever had a backdoor to that algorithm it had like a master key to open all doors, That's actually that infamous publication by the National Institute for Standards and Technology, NIST, recommendation for random number generation, and then describes this infamous dual elliptic curve random bit generator, dual ECDRBG. Here is the elliptic curve that they used. So in fact, you can go back to my old video and I talk about it in more detail. But you see, this is an equation very much like the one we have discussed. You have a second order polynomial in y on the left and a third order polynomial of degree 3 cubic polynomial in x on the right-hand side. And here is the prime number. Here's how many hours the US government has on their clock. See how many digits there are. So anyway, sometimes people ask, this is all very interesting, but it looks very abstract. What are the real-world applications? And so my answer to that is, there are applications. You can be sure of that. Or if there aren't yet applications, for example, of the type of questions we discussed regarding Shimura-Taniyama-Wei conjecture and so on, there will be applications. Mathematics always finds real-world applications. The question is whether we will be wise enough not to use it for evil purposes, which unfortunately has been the case with some of the applications of mathematics and science in general. Let's now go back and discuss modular forms. So I explained that this infinite product represents what's called a modular form. And this is an object of harmonic analysis. So it's a totally different continent of mathematics from number theory, where our counting problem originated. So what are these modular forms? It turns out that, as I explained in my sort of basic example of generating series, sometimes something which appears as just a formal sum of various powers of q with some coefficients, like this one, can be converted in something which looks much nicer. It's kind of a more compact expression, namely 1 divided by 1 minus q. So we have to be mindful of the fact that this equality holds only provided that q, the absolute value of q, is less than 1. That's when the series converges, right? And then it converges to this expression. With modular forms, the situation is very similar. Here we also have an expression of this kind. The coefficient of the first power of q is always going to be 1. It's kind of a normalization for this modular form. Then there will be f of 2, q squared, f of 3, q cubed, plus etc. Right? And it turns out that these expressions will also converge when q, absolute value of q, is less than 1. But in this case, it is important to take not just real numbers, but complex numbers. Now, as you know, complex numbers can be represented by points on a plane where the x-coordinate is the real part and the y-coordinate is the imaginary part of the number. So if you're interested in the numbers whose absolute value in the sense of complex numbers is less than 1, they correspond to a disk of radius 1.
It's got to be inside that disk.
So these numbers all can be viewed as points inside the disk. So now we get some geometry out of this. So what starts out as an infinite expression, as a kind of a summation of various powers of q with some coefficients, even though initially we write it as a product maybe, but eventually we can open the brackets and find out all the coefficients and so on. But now we also realize that actually this infinite expression has a well-defined value for any point inside the disk. And every time something like this happens, you ask whether this function that you get, because what we get is really a function, it's a rule which assigns to every point inside the unit disk on the complex plane some complex number, whether this function has any symmetries. And the modular forms are defined precisely by their symmetry properties. Now, before I explain what the symmetry property is, I want to discuss kind of a baby version of this, kind of a simplified version of this, which has to do with trigonometric functions. So in the case of trigonometric functions, a trigonometric function we consider as functions on the real line. So you have, for example, sine of x. Important property of a trigonometric function is that it is periodic. So if you add 2 pi to the argument, you will get the same thing, right? But in fact, then it means that if you add 4 pi, you will also get the same thing. If you add 6 pi, you'll get the same thing, and so on. So in fact, there is a whole bunch of symmetries of this function which are labeled by integers. You can add 2 pi times natural number, and the resulting function will be equal to the original for any natural number, or actually any integer. So that's what I mean by symmetry, that you modify the argument in some precise way, but as a result, the function does not change. So in this case, the symmetries are labeled by integers. And in fact, symmetries form what's called a group. So we can talk about the group of symmetries, and in this case, the group of symmetries is the group of integers with respect to addition. The word group here means that symmetries are not disjoint, that we can always take the sum or the difference of any two symmetries and we will get a new one. And this addition and subtraction is just the usual addition and subtraction of natural numbers or integers. And the mathematicians love to call it Z, which is sort of like a double line. That's the notation we typically use for the group of integers. The cosine function has the same symmetries. The cosine function has the same property that if you shift the argument by any multiple of 2 pi, you get back the original function. And this is a prototype, a blueprint for studying symmetries of various functions. So now let's go back to the context of modular forms. The difference now is that a modular form is defined not on the real line, but rather it is defined on the unit disk on the complex plane. However, it turns out that it also enjoys this kind of symmetry property. The corresponding group of symmetries is much more sophisticated. It is what is called SL to Z. Instead of explaining what it is, I will approach it in a more geometric way. So here we can encode the symmetry property of the trigonometric functions by marking these points 2 pi n. Here the point 0, then this will be minus 2 pi, then there will be minus 4 pi, and so on. And then here will be 2 pi, and here will be 4 pi, and so on. So the symmetries correspond to shifting the real line either to the right or to the left by an integer multiple of 2 pi, right? And we can try to represent the action of this group, or more precisely, it could be some subgroup. It's called the congruent subgroup of this group, but these are details, so let's ignore this for now. Instead of trying to describe how it acts, I want to produce a picture which is analogous to this picture, where the action of the symmetries of the real line, which with respect to which the trigonometric functions remain unchanged, is represented now on the unit disk. And for this, I will consult a very interesting book that I came across recently.
Oh, wow, look at that. Edward Frenkel.
Actually, the purpose of this book, which came out 9 years ago, was to give a kind of an exposition of the Langlands program for non-mathematicians. So if pretty much everything that I discussed today is discussed in more detail in this book. So if you're interested in this subject, then that's one of the sources. Also, various talks that I have given, like the slides that we have seen, which are available on YouTube, and so which probably you can link also under the video.
I will.
But I want to show you this this picture now because it's hard for me to draw it, but I will show you in. So see, this it talks about the Fermat theorem and the connection to the Shimura-Taniyama, and here is the equation that we discussed today, and the clock arithmetic, and generating functions, and all that. And so this is a picture I wanted to show you. So this is the unit disk on the complex plane, and this sort of triangles are the analogs of the intervals that you see on the real line under the action of symmetries of the trigonometric functions. This kind of curved, kind of hyperbolic triangles are the analogs of the what mathematicians call fundamental domains for the symmetry group of modular forms, or in one of the possible examples. It could be a picture a little bit different from that, but very similar to that. So it's kind of triangles, but curved triangles. They're triangles with respect to the hyperbolic geometry, non-Euclidean geometry, which one can set up on the unit disk. So that's the story of modular forms.
Okay. How are we going? Are we getting there?
Yeah, we're almost there.
All right.
And so now we have at least some sense of what elliptic curves are, what the counting problem for elliptic curves is, and that's on one side of the Langlands correspondence. Or in this particular case, we're talking about what's called the Shimura-Taniyama wave conjecture. And on the other side, we have modular forms. And now we have a sense of what those are. To put it simply, the Shimura-Taniyama wave conjecture is about the existence of a one-to-one correspondence between elliptic curves on one side and modular forms on the other side. And this correspondence satisfies this special property that the solution to the counting problem for a given elliptic curve can be read off of the coefficients of the modular form when you write it as a generating function in the variable q.
When I say to you then, what is the Langlands program? It is the toolkit and the methods and the conjectures and the algorithms to join these two parts of mathematics.
That's right.
That probably didn't seem like they were joined at all. It's finding,
That's right.
It's finding the hidden tunnels.
That's right, or bridges, or building bridges, you know. So, but you're right, a kind of hidden tunnel is maybe a better way to put it, because I think that even though we can now prove a lot of examples of this type of correspondence, I still think it is mysterious. I still think we don't understand the underlying reasons. So in other words, there is something beneath the surface, something hidden. There's some hidden cache which we still don't understand. Mathematicians today don't understand, which I think maybe in 100 years, 200 years, we will have a much clearer understanding. And people would, do a Numberphile video 100 years from now, and they say, 100 years ago, people didn't understand what was the reason for this correspondence? But actually, it's so simple. It is so obvious, So
in high school.
Yes, but now we don't see it yet. But it's important. So it's important to emphasize that there are these connections, and that there probably is a good explanation for this. But it's important to how can we come across those explanations? We can come across by studying them more deeply, in more detail, and considering the same kind of patterns in other contexts as well, you see. So in fact, the Shimura-Taniyama wave conjecture, which I have used to illustrate the general ideas of the Langlands program, was known before Langlands came up with his ideas. So he knew that this is kind of an example. So in fact, the Langlands program talks about much more general things than what we have discussed so far. And I wanted to just indicate what they are. So far, the correspondence that we have seen is between elliptic curves on one side, modular forms. And the correspondence is such that it matches certain numbers attached to objects of both kinds. On this side, you have this counting problem, and you get these numbers AP, which is basically number of solutions, mod P, more precisely P minus number of solutions. Whereas on this side, these are the coefficients of the modular form, coefficient in front of Q to the power P. So that's the prototype, that's a blueprint of how Langlands correspondence is formulated in the general context. So what will be the objects in general? So the idea is that actually what appears on this side in general is not going to be necessarily a curve, elliptic curve, or it's not necessarily going to be some equation. What is relevant to the side is something that has to do with a great French mathematician, Évariste Galois. So he was this French genius who died in a duel at the age of 20. But just before he died, he made these profound contributions to mathematics. He came up with what we call today the Galois group. The Galois group is a group of symmetries. you see, we have already encountered symmetries on the side of modular forms when we talked about symmetries of modular forms being similar to the symmetries of trigonometric functions and so on. But actually, symmetries also naturally appear on this side. We can call this side number theory side, and this side harmonic analysis side, right? So symmetries are actually essential on both sides. And on the side of what we see here as elliptic curves, or on the side of number theory in general, what we get is what's called representations of the Galois groups. Now, it will probably take us another bunch of videos to explain what this means, but I discussed this here. So this representation of Galois groups in chapter 8 of Love and Math. So these are the more general things, which in the case of Shimura-Taniyama reduce to elliptic curves, can be connected to elliptic curves. So it gives a much more, a kind of a simplified way of describing these objects. In general, we may not have a specific equation which is behind this object, yet they can be defined rigorously in number theory. These are the objects on the left-hand side, so to speak, of the Langlands correspondence, the number theory side. And the objects on the other side, on the right-hand side, are called automorphic functions or automorphic forms. These are the generalizations of the modular forms. And again, the idea is that there is a one-to-one correspondence between the two, or sometimes could be many-to-one, because sometimes it can be, depending on how you phrase it, sometimes it gets kind of more murky. But in the clearest examples that have been understood so far, one actually gets one-to-one correspondence. But just getting one-to-one correspondence between objects of two kinds is not so interesting, ultimately, because, you know, if you have both are two countable sets, so you get a one-to-one correspondence between two countable sets, so what? But what really makes Langlands correspondence interesting and exciting, and what makes, you know, allows one to use it as in applications, is the fact that under this correspondence, certain information from number theory, which has to do with Galois groups, gets translated to analytic information that has to do with automorphic functions. In the case of that we have discussed, I have explained what that information is. On the side of elliptic curves, these are the numbers of solutions of the cubic equation underlying this elliptic curve. And on the harmonic analysis side, these are the coefficients of the modular form. In general, this data can also be expressed. They're a little bit more complex, but they can be stated, you know, precisely what they are. And the beauty and the power of the Langlands correspondence is that under this correspondence, those numbers match, just like they match in the case that we have discussed.
If any link is found between any two continents of mathematics, that doesn't automatically mean it's Langlands. Langlands is more specifically links between the Galois groups and the automorphic functions.
Right. So, you know, I want to say something that links between different continents is a quite common occurrence in mathematics, and it's something which is prized, precisely because it indicates that there are some things which you don't see yet, which are beneath the surface. And if you look in the history of mathematics, that a lot of the great discoveries were made when mathematicians somehow stumbled upon this kind of links without understanding what they are, but eventually were able to find an explanation. And that was always fueled progress in mathematics. And so this is an idea which I like to call unification. So there is a certain sense of unity in mathematics, that even you know, subjects which appear to be far apart, in fact, are not so far apart. And so, you know, one of the simplest examples, just to illustrate what I mean, is the following. If we just talk about numbers, natural numbers, then of course we know the kind of the simplest way to introduce numbers is by counting. So you have 1 pencil, 2 pencils, 3 pencils. But that's not the only way. Let me show you another way. Give me a second. Yeah. And for that, I'm going to use a probe. You know, my dentist always complains that I don't floss enough. But you see, so my dentist will be proud of me if he watches this video. What you can do is you can also wrap the floss, this thread, on the finger. You do it once, you do it twice, you do it 3 times, 4 times, and so on, you see? So that's another way to introduce numbers. And the advantage of this is that whereas all these pencils are different, so in fact when you explain to children numbers, they say, but how can you all consider them as objects of the same kind? They have different colors. But here it's clearly something of the same kind, just kind of what we call winding number, how many times the the floss has wound up on my finger. And the second advantage is that I can do it clockwise or counterclockwise. And this way I can represent both positive and negative numbers, whereas I don't know what is a -1 pencil. But I know what is a -1 number. In this realization, I just go clockwise instead of counterclockwise. You see, so this is, for me, is a basic illustration of unity of mathematics. That the same concept, the same idea, namely in this case, a very basic idea of natural numbers, arises from two areas of mathematics. This, what we could call counting, is number theory, and this is what's called topology. The study of these windings and so on is, one of the illustrations of the field of mathematics or continent of mathematics called topology. And so ultimately, I think mathematicians always find it extremely exciting and fruitful to find those connections, to find different ways. You can think of this as different ways of looking at the same thing. It's like, if I have this, I can look at it from above, I can look from the side, and so on. So ultimately, the mathematics is a kind of a mysterious beast which we can observe from different sides. And to me, that those connections that we find, like the ones we have talked about today, are indications that we are looking from different angles at the same object.
And you tell me, like the Langlands program's finding all these exciting connections between representation of Galois groups and automorphic functions. I don't know what either of those two things are, and I don't want you to tell me because I won't understand, but you're telling me that those are two continents that are important enough for Langlands to be getting all these prizes. And
that's right. In 2018, he received the Abel Prize, which is considered as a kind of equivalent of Nobel Prize for mathematics. Is given out by the King of Norway. I was actually asked to give a public lecture about his work in Oslo during the festivities. One of the things that I want to mention is that, yes, today we talked about these two continents, number theory and harmonic analysis, and how this link between them enables us to translate seemingly intractable problems in number theory to much more feasible, much more tractable problems in harmonic analysis. But in fact, that's just the beginning of the story, because that was the original setup, the original way that how Langlands thought about these ideas at the outset. Right, so in the 80s, these ideas of Langlands program propagated to geometry, and so mathematicians were able to find the similar patterns, but in the study of things for complex numbers. So we talked about elliptic curves, for example, in the clock arithmetic, solutions modular primes. But you could also look at solutions in complex numbers, and in that case, elliptic curve will appear to us as a surface of a donut, as a torus. So it turns out that the kind of things that we observe in the original classical Langlands program can also be kind of carried over to that domain where you look at equations but now over complex numbers. And it's very exciting. And what is even more exciting is that physicists also observed similar patterns in the study of what they call dualities of gauge theories. Gauge theories is a mathematical apparatus of the standard model of the best theories of interaction of subatomic particles that we have. Although in this case we are considering what's called supersymmetric versions of those theories, which do not necessarily have direct bearing on our universe, but maybe have bearing on some other universes, who knows. In any case, they are beautiful mathematical gadgets, and in those mathematical gadgets we can observe similar correspondences like the one which we have discussed. In other words, this is just the beginning of a story. There are many other things, many other places in mathematics and quantum physics where similar patterns arise. So perhaps in another video we can discuss this, but perhaps that's plenty for for today.
Well, you made it this far. There's a good chance you'd like to see even more from Edward Frenkel. I'm going to link to a playlist of videos he's made here on Numberphile and a podcast he did with us, as well as a link to his book Love and Math, which is definitely worth checking out. All those links, everything you need, will be in the video description.